Great. Can I start? Fantastic. So thank you very much indeed, Maya. It's a really great pleasure to be able to talk to the conference today. It's a shame not to be there in your beautiful weather. It's not beautiful outside in Manchester, but yeah, as I say, it's great to have the opportunity to share some of our recent science. So before I start, I wanted to thank all of the people involved in this work. My work really is a collaboration between the microscopists who work in my group, the experimentalists who do the fabrication of the beautiful structures that I'm going to be showing you today, and also the theorists who are absolutely vital to allow us to understand what's going on in these systems. So I wanted to tell you about some work that we've been doing looking at 2D stacked heterostructures over the last year or so, particularly focusing on some aspects of twist and some air sensitive materials. And I'm going to apologize in advance. I'm going to be on quite quickly to fit into the 15 minutes, quite a lot of different things. But again, I hope that you'll forgive that. So I'll do two aspects in the 15 minutes. First, looking at the twisted transition metal dichalcogenide bilayers, reconstruction in those systems, and then looking at degradation of air sensitive crystals, the post-transition metal chalcogenides and tantalum disulfide. So to start with, many of you may have seen the beautiful images that have been produced already in twisted graphene and graphene hexagonal boron nitride bilayers. These are a hugely exciting system from the point of view of the fundamental physics. They have demonstrated a wealth of interesting properties. And if we just look at what's happening structurally in these systems, when you take one graphene layer and put another graphene layer on top with a small twist angle, that's maybe a degree or less, then we get a reconstruction of the system to produce perfect commensurate stacked lattice separated by these misfit dislocations. And that's what you can see in this image here, which is not my work. This is the work from the Yu et al. In Nature Materials in 2019. But there's a number of other beautiful work looking at these types of systems. However, when we started to consider this back in 2019, nobody had reported what might happen when you take two transition metal dichalcogenide layers, that's molybdenum disulfide, tungsten disulfide, tantalum diselenide, all of those, and twisted them by a small angle. However, in 2019, in March, Nature had four papers within a single issue demonstrating the really exciting physics that you can get from these types of twisted systems. But none of those papers looked at what might be happening with structural relaxation, and we know that structural relaxation affects what we get in the electronic structure. So to introduce this, I just wanted to reflect a little bit on the structure of these transition metal dichalcogenides. You can see that illustrated schematically here. And unlike in graphene, we have two different types of lattice that we can produce when we twist a bilayer transition metal dichalcogenide. So if we add the second layer with the same orientation, and what I mean by same orientation, if you look at in the cross section, as you can see here, we can imagine that the metal chalcogen because producing like an arrow, and if we have the top and the bottom layers pointing in the same direction from the point of view of these metal chalcogen arrows, then we end up with a parallel stacked lattice, and that's what I'm illustrating here. So this is with no reconstruction and a relatively large twist angle, but just to illustrate the different types of stacking that we see. We can get metal on chalcogen. We have regions where we have chalcogen on chalcogen, the chalcogen on metal, and metal on chalcogen. We get the general idea. We can classify these metal on chalcogen on metal as being the traditional 3R type stacking that we expect in these systems. And then we also have these chalcogen domains, which we know are unfavorable. So we've then taken these systems looking at metal, various different metals, so tungsten and molybdenum. And you can see that they do indeed reconstruct. So the previous images I showed you on graphene were using the transmission electron microscope. These images are taken in the scanning transmission electron microscope, where we just tune the angles such that we're picking up all of this diffraction information so we can see the domains and the dislocations that are separating these domains. And we can see that we get a similar type of triangular lattice reconstruction, where we have the more favorable 3R type stacking regions in large, and between them we have these dislocation type regions, and we can see here, and we compare that to the modeling, and that makes complete sense. We understand that the 3R type stacking is the most dominant, and so we want to enlarge those regions. If we look now at an anti-parallel stack, so that's where we take the top transition metal chalcogenide layer and twist it by 180 degrees, and then apply a very small misorientation. So the lattice misorientation between the two layers will be 181 or 179. You can see we then get different types of stacking, and we can classify this now into regions that are this 2H type stacking, which is the standard stacking you'd expect in a perfectly aligned transition metal dichalcogenide. We also get regions of metal-metal stacking and chalcogen-chalcogen stacking, which again we'd expect to be unfavorable. And this leads to a completely different domain structure that really haven't ever been seen before. So because these 2H domains are by far the most stable region, and that's what we can see here, the metal-metal regions are more stable than a completely incommensurate lattice, but not as stable, then we end up with this type of reconstruction here. So as you can see, we have these large 2H type domains, which are kind of hexagonal, and they're separated by these small metal-metal triangles domain regions. Now, I mentioned that we're doing this in scanning transmission electron microscope. I should have said that this allows us to then only slightly change the settings and get also atomic resolution scanning transmission electron microscope images. And this really is a nice way to highlight the different stacking domains. We can zoom in on the different stacked regions, and of course, matching to simulations, really understand what's going on at an atomic level, even when we've got defects. So we've looked then at different twisted transition metal chalcogenide bilayers for different angles. So the different angles you can see here range from about 2.5 degrees misorientation, anti-parallel stacking. And here you really don't see very much reconstruction at all. But when we start to get down to these much smaller regions, you can see that when we have an angle of just 0.75 degrees, we have a very large 2H domain of perfect commensurate stacking separated by these dislocations with these type domain regions. And even if we make the angle much, much smaller, these domains seem to have a fixed size of just about 5 or so nanometers. Whereas as we get that angle smaller, those 2H domains are able to get larger and larger. So if you can see here, this is your unreconstructed simulation on the right. This is the reconstructed simulation, and this is the experiment. It's a bit difficult to see that comparison because of the large scale of the data. These domains are of the order of tens of nanometers or larger. So when we zoom in, we've overlaid now the experimental data in black and white with the theoretical prediction, which is in red and blue. And you can see there's a really good match between those two. However, the scanning transmission electron microscope here hasn't got the sensitivity to be able to show the out of plane types of separation. And we know that these types of different stackings do have differences in the interlayer separation of the order of about 50 picometers. So we went to try to use the AFM to be able to try to look for this atomic force microscopy. However, this is really on the edge of what is possible with atomic force microscopy measurements. And so you can maybe see that in the parallel stacked regions, we're starting to see some sort of triangles, but it's really not terribly convincing. So instead, we were looking at the conductive atomic force microscopy. And here the domain structure really lights up like it did in the transmission electron microscope. And the reason for that is that although both of those triangular domains are 3R type stacking, they are flipped by upside down effectively relative to each other. And that results in a fact that it is easier to be able to tunnel into the one which is one way up as opposed to when you've turned it upside down. So in fact, that's a relatively large factor. As we can see here, we get an increase of about 1.5 times easier to tunnel into that region because of differences in the electronic structure within these two materials, two different stacking upside down. Okay, so then we started to look at the anti-parallel stacks. Those were those ones where we had the hexagons and also the little triangles. And here we were really surprised because we found that the type stacking really lit up in the conductive atomic force microscopy. And that led all of us really to scratch our heads for quite some time to try and understand that. It's not the same effect of this differences in the electronic structure. In fact, the electronic structure that we get here is very similar for those two domains. That doesn't explain what we get in terms of the differences in the tunneling current. And the 2H structure has an inversion symmetry, so there isn't a difference between the different 2H type domains. And so as I say, what the theorist then went back to the drawing board and looked at the fact that here we're getting a piezoelectric charge distribution, which is again being visualized in this conductive atomic force microscopy. We don't see that in the 3R type domains, and that's due to the fact that here we've got differences in the way that these two behave, and you can see that also right at the boundaries that we see for these types of materials, where we have, this is an edge and the twist has got some reconstruction happening at that edge and it's constrained, so we've not got that full Kagome lattice, we've just got this 2H type of 2H type of dislocation running along there. Fantastic. Okay, so I know I went through that very quickly. I'm happy to answer any questions, but I just wanted to highlight some other work that we've been doing this year. First of all, looking at the post-transition metal dichalcogenides, these caused a huge amount of interest over the last 5 to 10 years because of their optical and electronic property behaviors. Particularly in the area of second harmonic generation, is very interested in Manchester, similar with the single photon emission. These are slightly different from the materials that we might be very familiar with as 2D materials, because they have two metals, a sort of double metal layer sandwiched between these two layers of chalcogens. And that's what we can see here. Again, we get both the 2H and the 3R type stacking. So if we have a look at these, we've seen that they do degrade. They degrade quite quickly as a function of time, certainly over hours when exposed to air. And so I'm just going to mention that these have been produced in an argon glove box, and they're sandwiched together in an argon glove box, transferred onto a TEM grid, and then they're protected by two layers on top and bottom graphene before we put them into the TEM, and that allows them to be as pristine as we can make them at the moment. There's been a huge development in Manchester, and Roman Gorbachev has now produced an ability to do this stacking in ultra high vacuum, and so we're really looking forward to the exciting types of new materials that we're going to be able to look at when the exfoliation happens in UHV. However, here we can just look at the post-transitional metal chalcogenides. These do have defects in them. We are producing defects with the electron beam, even when we use low energy, especially when we've trapped contamination between our two graphene sheets. We see a huge increase in the amount of structural degradation that we get in these materials when we have oxygen vacancies or water trapped under the graphene. We can characterize what we're getting for these types of defects. This is for the monolayer gallium selenide. Here we see vacancies both in the metal sites and the chalcogen sites. In gallium selenide, the selenium sites have been substituted by oxygen, and we also see oxygen uptake for regions of degraded structure. Similarly, in indium selenide, we see both metal and chalcogen vacancies, but here we don't see the selenides being replaced by oxygen. And that's reflected in the same when we do low magnification elemental mapping. We don't get oxygen uptake in the degraded regions. Differences again observed in the larger scale defects. We see these triangular type defects, a little bit like we get in hexagonal boron nitride. We see these triangular defects in gallium selenide, whereas indium selenide has a more molybdenum disulfide type defect structure, these long strings of defects. Molybdenum disulfide, that's because the sulfur defects dominate. So here we're going to assume that it's the selenium defects that are dominating, giving us these line defects, and that fits with what we can see in the simulations. But I would say that this is really not fully understood why these two isostructural materials are behaving quite differently in terms of their extended defect properties. We see that both have differences in stacking. I'm just illustrating it here for gallium selenide. We get this 2H type stacking, and that goes off transitions to an AA type stacking. We think that's been produced by our mechanical deformation, so during the exfoliation process, but that's really interesting because these types of stacking do not exist in the as synthesized material, and they should have very different optical properties. So understanding that these might be present in your devices is really important, and being able to tune these, which we've shown you can do now by exfoliating along a particular direction, at least we've shown that in graphite, I think is a really interesting area for a future route to tuning the properties of these post-transition metal monochalcogenides. Okay, last 2 minutes, Maya. See you. Yeah, great. I wanted to move on to tell you a little bit about tantalum disulfide. Now, this was a weird material. Most of our air-sensitive two-dimensional materials degrade as a function of time. This one was improving as a function of time. Specifically, the superconductivity, the critical temperature was getting better when the samples were left and aged over days and months. And so the physicists came to us. This is work from Professor Irina Grigorieva's group. They came to us and said, well, why is this happening? At the same time, they asked the theory group in Antwerp, and they had come up with this principle that if you substitute oxygen into the tantalum disulfide lattice, a little bit like we'd already seen in the gallium selenide, that if you substitute oxygen into the lattice, you should be able to explain this improved superconductivity. So the question was, can you see the oxygen substituted into the lattice? Unfortunately, the difference between tantalum, oxygen, and sulfur means that it was not possible for us within the graphene encapsulated structures to distinguish between a sulfur vacancy or a sulfur site and an oxygen substituted sulfur vacancy. And for that reason, we had to move away from the imaging. We tried annular bright field, we had lots of different types of STEM imaging. We weren't able to see the single oxygen vacancies in the lattice conclusively. So instead, we did a study using electron energy loss spectroscopy. We looked at the material as a function of time, so day 1, day 2, day 3, up to 3 weeks old. And we were able to see that there was indeed an increase in oxygen. That increase in oxygen was much greater in the tantalum disulfide than it was in the encapsulating graphene sheet, so it wasn't just a buildup of contamination on the surface. And by analyzing the shape of that oxygen K-edge, we were able to separate the fact that you had both an oxygen component, which was crystalline, and an oxygen component that was amorphous. So the presence of a crystalline oxygen components really does suggest that that oxygen was indeed substituting into the lattice and is in agreement with the theory. Okay, so in conclusion, I hope I've shown you some of the things that scanning transmission electron microscopy can do to support the development of 2D heterostructures and a better understanding of the different types of properties that we can get in these systems. I'd like to thank all my collaborators, the funders, and of course you for listening. Thank you very much.
Thank you, Sarah, that was wonderful. We have 2 questions in the chat that I'll ask you to answer during the next talks. We'll also have the discussion at the end. And we have time for 1 question if somebody wants to ask just now.
Can I ask?
Yes, Haggai, please.
You have in the oxygen onset, in the oxygen edge, the plasmon loss is very different for the 2 different spectra. Does that say anything on the? Can you show it was maybe one before the last? Or?
Yeah, let me try and go back in the slides. Okay, here, yeah.
Yeah, on the bottom right. So you see quite a different plasmon loss, I would say. I think so. I'm not sure.
You mean the extended loss? This.
Yeah, around 560.
Yeah.
And does that say about the position and where it is? Yeah.
Oh, that's a really interesting question. I don't think we've looked. So that's a great point. So no, we haven't tried to yeah, all we've done really is to have a look at these 2 different shapes, which we can extract out, and they, when you compare with lots of different crystalline structures in the literature, that's what you'd expect for a crystalline as opposed to the oxygen amorphous edge. But no, we've not tried to have a look and see if we can therefore verify what the bond distances should be in tantalum disulfide substituted with oxygen. And that's a really good idea. We should have talked to the theorists about trying to match those 2 together and potentially do some simulations from their calculated structures. So that's a really good call. Thank you.
Mm-hmm.
Okay, so as you remember, at the end of the session, we've got some time for discussion, and we will sure continue this, and whatever you can answer in the meantime in the chat is also good. So I just want to thank you again, Sarah. Please stay with us. And Adi is now sharing. I want to introduce Adi as well. So Adi comes, of course, from the Bar-Ilan University. And as always, you meet people when you do your PhD and your master, and then they keep on coming again and again and showing these wonderful presentations when you become PIs. So Adi, it's really a pleasure. Please just show us the newest. Yeah. You are still muted. You need to unmute.
Sorry. So thank you very much, Maya, for the invitation, and thank you very much for setting up this very nice conference. It's a pleasure. Thank you very much, Sarah, for your nice talk. And actually, it's I think it just continues to talk about cathodoluminescence after you show some ILS spectra. So today I will share with you some of our latest results on cathodoluminescence nanoscopy of various of plasmonic structures. Some of them are well defined, and some of them are disorders, as you will see. So I will start. So in general, the motivation of my group is to study light-matter interaction at a nanoscale, where the idea is to form hybrid photonic or plasmonics material based on strong coupling between molecular system emitters and plasmonic structures when you have confinement of the electromagnetic field. To get this high confinement or deep subwavelength confinement of the electromagnetic field, we use plasmonic structures, either well-defined or what I will show you as well, nanoporous metallic networks, which is a sponge of a carpet of a sponge of hotspot. We do it to basically to change photochemical processes in molecular system and to use these structures for photocatalysis. Other things that we do as fundamental science is to study energy transfer processes between molecules which are immersed in this plasmonic field. And I just lead you to several examples. So just a second. So here, for example, you see that when we put carbon dots on C dots on plasmonics array, even if they have the same physical properties, since they have some different functional groups, we see different colors once they are deposited on the array, even if it's just 5 to 10 nanometers. This is collaboration with Raz Yelnik at Ben-Gurion University. Another example is what you see here is transit absorption of molecular system, which once just deposited on a silver film, and once it's deposited on plasmonic resonator, and once they couple together, you basically get a new molecular system, as you can see by another spectroscopic mode. Another example is to use these nanoporous metallic networks, as I will show you later on, as a sponge of hotspots to enhance photocatalysis. But for all of this, what we need is basically a hotspot, and we need a very strong confined electromagnetic field. And usually we used to see very nice cartoon of either bow tie structure or lightning rod effect, where we have a very strong electromagnetic field in between. It's very nice in the illustration, but in reality, it's some structures that it's quite difficult to fabricate. And we adopt a bit a different approach. So what we do, instead of control the plasmonic structure by the size and the shape, as we all know, or propagating surface plasmons by periodicity of the array, what we can do also is to design these hotspots on a flat, onto the surface between the cavities, actually, as you will see in a second, or in this example here. And we use hybridization in order to design these hotspots and to control them either by polarization of the incoming field, by the distance between the subunits, and so on and so forth. Okay, so this is, just a second, one of the examples. So let's say that our subunit is a single triangular hole, And once we have two cavities which are in proximity to each other, they don't have to be that close to each other, but since we have the conductive metal, they couple to each other. And once they couple to each other, as the distance between them is, if the distance between them is varied, then you will see different colors, which actually tells you that we have different mode. It's adapted from the hybridization model of molecular orbitals. So again, if we have a charge distribution around a nanoparticle or a cavity, once they are close to each other, we change this charge distribution, and we have either bonding states or anti-bonding states. And once we change the polarization of the incoming field, we can change this charge distribution and have basically other energy mode of the system. So as you can see here, once we change the polarization of the incoming field, we can have different hotspot at different frequencies. We can now elaborate these things and use, instead of only holes or nanoparticles, we can use basically these large scale metallic 3D metallic networks, which is building blocks are either nanoparticles or holes, and by that have a carpet of a hotspot, as you will see in 2 minutes. What is nice about this large scale metallic electrode is that you can see macroscopically the optical properties of these networks. For example, gold as a color, as a purple color, it depends on the average size of the particles. Silver has a kind of yellow gold color. And so basically we have a hotspot at different frequencies, as you will see by cathodoluminescence. And we have these big holes, multimodal holes that enable us to use this sponge for photocatalysis, because it has a place for host to host material. We can do it in different metals, of course, but this is a different talk. Just an example for you that you can look later on the reference. And okay, so again, the idea is that to use either well-defined plasmonic structure to harness the electromagnetic field at different frequency, and to control it by either polarization of the incoming field or the distance between these holes. We can either control the frequency, as you can see in this example, but also by changing the parameter of the subunit. The subunit is just a single triangular hole. We can also control the amplitude. What you can see here is an example of the metallic network. And this is cathodoluminescence scanning, and you see that it has a multiple hotspot, a different wavelength at a sub-wavelength distance as well. So basically, it's a sponge of hotspot. So at the end, we want to map the hotspot to design this plasmonic structure and to understand basically what's going on, what is the model of hybridization, and so on and so on and so forth. But we have a problem, because we have a strong local field over a broad optical range from the UV to the IR. And these strong fields are confined to sub-wavelength volume. So for sure, we cannot use optical measurements which are diffraction limited. They are not adopted for such characterization. And once we measure these structures, especially the metallic network, by just linear optical measurement, it's all average out and result in a broad spectrum, which doesn't really reflect the properties, the optical properties of the plasmonic structure. Near field optical microscopy is also very kind of difficult, but is limited in this type of topographic network, for example. And if we would like to get information about the local density of states, we can use cathodoluminescence, which at the end, the intensity of the cathodoluminescence, the intensity of the photons reflect the number of available photonic states. So this technique, which is a sister of the electron energy loss spectroscopy, it's undergo under the electron microscope. And because we use localized electron beam, we can have a nanoscale resolution. Also, the localized electron beam is considered as a white excitation source. So just to say, in cathodoluminescence, unlike EELS, basically we have photons which are scattered by the sample and are collected, and these photons reflect the efficiency of the plasmons which are decay into radiation. From cathodoluminescence, it's possible to retrieve the full spectrum from each pixel of the scanning and from each pixel of the scanning, as you can see from this example. So this is the optical image of this structure, a cross structure, where you can beautifully see that we have a hotspot which located between the cavities, and basically the high electromagnetic field is concentrated between the cavities here. You can see also the antinodes, much like molecular orbitals. So I will take you to much simpler plasmonic structure with just two cavities that are coupled together. And as you can see here, we have a confined mode between these two cavities, which we can control its frequency by changing the distance. Once we take the cathodoluminescence spectrum at different wavelength, we can understand the mechanism of this coupling between them and construct other structures like the smallest micron size RGB that we know. Again, and in this RGB pixel, we have a confined electromagnetic field onto a flat surface. And for us, it's important because once the molecular system is deposited on the surface, it's easy to control the energy transfer processes between the two.
You've got 2 minutes, Adi.
Okay, wow, okay. Of course, that the metal type is also make a different, as you can see in this example. Once we go from silver to aluminum, which fits more to the Drude model, you see the hybridization is more pronounced, and we cannot retrieve exactly the plasmonic structure easily, but we know it. I will go quickly to the metallic network. Sorry for that. Just wanted to show you that it's also correlate with second harmonic generation mapping, because indeed we have the hotspot in between the cavities, and we can use it, of course, to application like surface enhanced Raman spectroscopy to detect pesticides at low concentration as 10 to the minus 10 molar, and due to these hotspots. And now just with the 2 minutes that's left to go over the network. So what is nice about this network that it's not anymore well-defined structure. So it's very difficult to correlate between the network structure and the carpet of the hotspot. We have a multimodal plasmonics modes all over, either in the holes or in the particles. We definitely see that the particles are more enhanced. We can see that we also have a nice phenomenon of hotspot at different frequencies at sub-wavelength distances, as you can see from this example. So at about 100 nanometer or 200 nanometer, you can find over the network, you can find basically all the plasmonics mode over the visible range. Once we scan a specific area, we can see that this hotspot can be switched on and off depending on the wavelength. What else? And the other thing that I will finish is the connectivity between the different elements which play an important role. For example, if we have an element which has no connection, only one connection to the network, we see a very clear localized mode, whether when we have a kind of octopus structure which is connected all over, the energy is dissipated and we barely see emission at this region, which reflect the optical robustness of this network. And with this, I will finish. I will thank you. I will thank, of course, to Atolite, which will allow me to do this measurement with them in Lausanne. My group, so the work of the metallic network was done by Racheli Ron. The other plasmonics device by Dr. Elad Segal already for my group, Omer Shavit, Dr. Adam Weissman. Also, we saw some work by Lee, was already working other places. And I, again, would like to thank to you and the money sources. So thank you very much.
Thank you, Adi. I think that you have a few questions in the chat that I'll be very happy if you can answer when we, because of lack of time, we'll go to Ido and continue with the next session. Okay, please don't forget at the end, we also have some discussion. So if somebody wants to get more interactive discussion, then Adi will be here also later. So Ido is coming from the Technion. He will use also a TM, but for some completely different other things than what we usually do. So please just show us your work.
Awesome. Can you hear me okay, by the way?
Yeah, everything is great.
Awesome. So thanks, Maya, for the invitation. I'm really glad for this, for having this session. I was actually looking forward to hear about these results and heard about her work from Atolite and was looking forward to it. I'm actually going to talk about using something that is in many ways related to photoluminescence, but in reverse. We're working with a TEM and having light coupled into it, and then measuring with EELs how the light alters the electron microscopy. So we are using light to alter the EELs, and we'll see how we can do interesting stuff with it. But my group is now running for almost 3 years at the Technion. The microscope is running for about 2. And we have, I think, quite a lot of exciting stuff happening that we were working very hard to achieve. And I'm really glad for my group and for the hard work everyone put into it, that we're starting to see the first fruits over the last couple of months. And I'll show you a few of them in the little time we have. The general idea is this combined system that has a TEM combined with laser systems, ultrafast femtosecond pulse systems that allow us to study a range of effects. And I'll first, I want to say a few words about why we like electron microscopes coming from areas of physics and electrical engineering. And I think that one reason that I like electron microscopes a lot is how it allows us to explore fundamental questions in physics. And that's something that I want to say. There are 2 reasons for this. One is that the electron microscope allows us to see quantum effects and do quantum experiments in areas that were for many years considered classical. For example, if you think about sources of light, radiation, synchrotrons, free electron lasers, all of those are based on the same electrons we use in the microscopes, but are always described classically for many, many years. And what we see is that we can imitate those kinds of experiments and do them inside a microscope and use quantum mechanics as the way to describe them. And we find that quantum mechanics is necessary to describe them. And another reason we like electron microscopes is that we can study physics that is for many years considered unique to bound electrons, like electrons in atoms, electrons in quantum dots, and see analogous effects that are happening now in electrons that are free. And we can still control them in a precise enough way so we can bring them into cavities next to plasmonic structures to make them make individual discrete transitions like bound electrons do. And those kinds of effects, we can now do them with free electrons and imitate a lot of the ideas that are very well known in atomic physics, and suddenly find them in a completely different place where electrons that are relativistic are playing a role. And that's, for us, the general reason to do electron microscopy. And I want to bring a few examples throughout this talk of the kind of experiments we can do in microscopes of this type. And one example is that we can use the electrons to generate radiation. And that is, of course, very well known in cathodoluminescence, but also in EDS, in X-ray spectroscopy. And what we did here is that we used the microscope as a way to extract efficiently X-ray radiation. We're using van der Waals materials. So that came from a few collaborators, most of them from the group of Efrat Lifshitz at the Technion, where those van der Waals materials are interacting with the electron in a way that causes the electron to modulate the bound electrons in the material and create a set of dipoles. You can think about it like an antenna that is created along the trajectory of the electron, where different atoms along this antenna, different layers of the van der Waals materials, are modulated in a different way, so they all radiate in synchrony. And then the radiation we get, instead of being the typical material characterization that EDS gives us, is suddenly something that is created in a synchronized way by the electron driving them. And this is an example of the EDS measurement, that we look at the radiation emission as a function of the electron energy. And we see that by changing the electron energy in the microscope from 60 kilovolts to 300 kilovolts, we actually change the location of the X-ray resonance. What we get here is a tunable source of radiation that can be created with van der Waals materials. And we also find that the actual composition of the van der Waals material, this is the example for WSC2, but we did that for 6 different van der Waals materials, is giving us precise control over the behaviors of those peaks, the angular spectrum of the X-rays, and also the spectrum of the color of the X-ray. And I think that's one really exciting example of the kind of physics we can do using electron microscopes as tools for proof of concepts. And on that, there is also a Clio talk that Michael, my student, gave on this that is still online now with Corona, if you're willing to hear more. So let me bring a few more examples that I'll use I'll discuss the rest of my talk. One is that electron microscopes, which we're typically using to image the material, the shape of matter, can also be used to image the shape of light. We can think about them as near-field optical microscopes. And what we see here is an example I'll discuss in a few slides of how we can use them to look at the distribution of the field that is excited externally into the microscope. We're now also exploring theoretical ideas coming from those experiments. For example, the idea of whether we can imprint the information of a qubit on our electron and then use the high quality behavior of those electrons to control and implement any quantum gate on the electron. We recently created attosecond pulses from electrons. This is causing an electron to split. The same electron wave function splits into, in our case, hundreds of even a few thousands of locations in time. And what I find today the most exciting looking forward, this is a work we placed on arXiv a couple of weeks ago, is whether we can use an electron in a microscope to bring a new kind of information on materials, not just how they look like and what type of excitations we have, but also how we measure the quantum properties of those elements. If we have an excitonic material, it has a certain T1, T2 decoherence time, how long it takes to decohere. Can we use an electron microscope as a tool to extract this kind of information from materials? And we propose a scheme with which one can extract information like T1 and T2 from the material we're working on. And I think that generally combining laser light into electron microscopes is opening a lot of possibilities for new analytical capabilities in electron microscopy. So I'll use the couple of minutes I have to show you a few examples of what we already showed in this. And this all is centered around this system illustrated here, where the electron microscope is triggered by a UV pulse that is causing the electrons to arrive in a synchronized way, which we can control and trigger. And they're also coming in the form of a pulse. And then we'll put different kind of samples and also trigger them with light sources, and then measure the electron energy distribution with EELs. And that's how it looks like. It's a marriage of a laser system sitting on two optics tables from different sides of the microscope, all floating together around this column of the TEM. And the laser system itself is quite complex and getting more complex every day in my lab, because we want to do more and more things with it, coupling the laser light into the column from the top port here, which we actually placed there because we extended the height of the TEM by about 50 centimeters to have enough space to put all the optics into it. And the second one is coupled into the microscope from around the sample height. So back to this system, what we're going to do is introduce different kinds of samples into the chamber and ask what's going to happen. And the first I want to discuss in that context is what happens if we put a photonic cavity. In many ways, like plasmonic structures that Adi showed, we can introduce different kinds of photonic crystal structures. And the first experiment we did in my lab was taking membranes made from silicon nitride that are having those periodic sets of holes. Those are used in biology for testing different kinds of samples. But for us, the periodic structure is actually a great way to trap light, because they create different resonances with specific colors of light that allows us to trap light for a certain period of time. You can think about it a bit like a cavity, which is illustrated here at the center, where light is staying trapped inside the cavity for a period of time. That actually happens in very thin structures like photonic crystals. And then the electron comes in and interacts not just with the sample, but also with the light trapped inside. And the microscope allows us to control this interaction with many degrees of freedom, from the tilt of the sample to the color of the laser light, the polarization, the arrival time of the two pulses. And with all of those degrees of freedom, we can get a lot of information about what's going on inside. And here's a summary of the different experiments we did, where what we are measuring here, each pixel in this plot is a separate experiment we did, where the idea is that we change the wavelength of the light and the tilt of the sample, so we can control how exactly we interact with the sample and with what color. And then we ask how strong the interaction is going to be by looking at the peaks of the EELS interaction. The stronger the laser field trapped inside, the more peaks we see in EELS, the brighter the point we put on this map. And then what I think is really wonderful, we see here in this map the photonic crystal band structure. It looks a lot like electronic band structures, but here, this is not for the electronic inside, not for the electrons, but for the light modes trapped inside. And more than that, we can choose a specific point and not just resolve how much the EELS shows us, but also do FTEM. So look at the images on filtered electrons by EELS. And then from those filtered electrons, extract how the light shape looks like. So we choose specific points here on this band structure. And for each of them, we can image how the light looks like on the sample. And those are giving us maps of the shape of light. And together, this is creating the ability to do near-field optical microscopy, which is a field that is today very strong in plasmonics, in 2D materials. What the capabilities we bring into this field are the resolution of an electron microscope. We so far have about 10 nanometers spatial resolution. We can probably do more and even go under 1 nanometer. It depends mostly on the sample today. We have a spectral resolution that depends on the ability to tune the laser, angular resolution from the stage itself, temporal resolution from the duration of the electron pulses, and also polarization resolution. And all of those, we see different ways to improve. And all together, they bring us into a new state of the art in near-field imaging of light. And if I look back on where this is coming from to develop this capability, what we
2 minutes.
Okay, so I'll just say briefly that we build this capability based on a set of developments that happened over the last decade. First, with the work of Ahmed Ziwel in 2009, where he showed this concept he called photon-induced near-field electron microscopy, how to use light to improve electron microscopy. And this is the first paper that showed this kind of behavior. It was 2009. It was at first unexplained and then showed in 2 theory papers in parallel in 2010. What brought me into this field is an idea that was developing this and showing how it connects to quantum optics in a very elegant way by causing the electron to perform a quantum walk on the ladder of energy levels. And this is a Roper's group work from 2015. There were a couple of other contributions by Carbone, Baum, Van Hart, and others, also theoretical contributions by other groups. And I think what is for us with the introduction to this field is our experiments from 2019, where we published this back-to-back with Roper's group on looking into the interaction of electrons with photonic cavities. But it's today becoming a growing field with more and more groups jumping into it. And of course, I can give a longer talk on this. I just want to summarize and say that for us, the frontiers now is to push the interaction to be as strong as possible. And for this, we're looking into an electron energy distribution like EELs. And in a regular interaction, what we see, this is the EELs picture now, is that the electron not only loses energy, but also has the ability to absorb energy. That's why the EELs here is symmetric on both sides. When we increase the intensity of the laser, we see multiple peaks, like you see here on the right. So there are multiple peaks on both the gain side and the loss side. And when we match the interaction precisely, and that's really the frontiers for our group, we find that the EELs completely change. You can no longer identify what is the zero loss peak, because it becomes one of many peaks along this plateau of energy peaks that is extremely long and broad. And this is the frontier of extreme interactions of electron and light. And there is a series of things we're doing with this, but I'll just show you one example that I think is really exciting, which is this idea of doing accelerators, electron accelerators on chip, which is a project that is being pursued by Erlangen and Stanford for a couple of years. It's supported by the Moore Foundation, of how to use silicon technology to develop electron accelerators on very small scales and pump them with laser lights. And what is now possible inside the TEM is to mount those accelerators, chip scale size structures, sideways in a microscope and bring the electron to graze the surface. We send it into channels. And here is what's actually happening right now in my lab. Those are beautiful electron beam lithography structures made in Germany that those are SEM images where we send the electrons through those channels. See the yellow line showing how the electrons pass through between those columns and are then interacting with light inside those structures, which is giving us extremely efficient interactions. And I think with that, I'll conclude, and I'm glad to take questions if we have a few minutes. I think there's a lot of stuff very exciting that we can do with playing with light inside electron microscopes. And thanks Maya for the opportunity.
So thank you, Ido. That was wonderful. We have time for one short question, and if it's not short, okay. Ernesto asked in the chat what useful information it provides. Maybe you can.
So, of course, it depends on what sample. But here's one example. When we look at regular EELs and we want to see a plasmonic resonance, we typically have a small peak, right? It's not always easy to observe. Same thing with excitonic resonances. And the ratio, typical ratio between a good plasmonic resonance peak to the zero peak will be 1 in 1,000, let's say, for surface plasmons. Sometimes it's a bit better, often it's much worse. This is always a spontaneous effect, the electron emitting some excitation, creating an excitation of a plasmon. What we do when we bring the laser in is that we stimulate the entire process. So we can make the peaks that we normally think about as very small, we have to subtract the zero loss peak, we make them significantly larger, as big as the zero loss peak. And that makes us possible to observe EELs peaks in scenarios that are normally not observable, and it makes it much easier to do. So it stimulates EELs in a very efficient way. So samples that normally are not efficient enough for EELs will here be observable. We'll be able to identify those features. And that's one example that I think is good for as a highlight of what we can do.
Thank you.
Okay. Thank you, Ido. We can, if you want to post more questions in the chat, then all the speakers will pay attention and answer. And I think that we'll move to Sydney, right? You are the next one. I don't think that Sydney needs an introduction. I'll just say that it's always a pleasure to meet those people that taught you a lot about surface science, doing this new stuff. So I'm looking forward, Sydney, please.
Okay, thanks a lot, Maya. So after all these really exciting things, it might seem kind of bizarre to be talking about Flint, but the fact is that recently, in the last few years, these cutting-edge nanoscale techniques have really been revolutionizing fields like archaeology and geology. And my colleague, here I get this going. My collaborator, Flippy Natalio, is really one of the people who's been moving this in a really amazing way. I'd like to also acknowledge Irit from the Weitzman, Thomas from Brazil, and Adrian from the ISPEC in Germany, who worked with me on some of the scanning probe results I'm going to be showing in this talk. In the bottom of the slide here on the right side, you see the area here in Israel, in the Negev Desert, Nachal Tzin, where these samples were taken. So this rock you see down on the right-hand side, that is actually not flint, it's chert, but I think all of you have heard of it. They're both really very similar. They're marine sedimentary rocks. They're composed mostly of silicon dioxide, but they also have organic components. And it's this hybrid structure which gives them their unique fracture properties, which is the reason that flint was so widely used for tools and weapons, and it's very useful in studying early hominid behavior. And because organic component, which serves like a thermostat for early environments, it's important also for paleontology and geology. So what I'm going to be concentrating though is one particular component, that organic component in this stone, which is these micropools, which originated from microbial colonies and were preserved by being entombed within the flint. I would like to also add that because of this complex structure, it's really important to be able to analyze using an in situ technique, which is non-destructive, and you can correlate physical chemical behavior with a certain location in the sample and a certain morphology. So the organics have a role also in the formation of the flint. It was proposed that these amino acids and peptides, they interact with the silica gel as it's crystallizing, and through their interactions actually help it form the crystals. The organic material appears in essentially two different forms. One is an intercrystalline form, which you see here in this ILS image, which is largely amorphous carbon. And that's composed mostly of kerogen, which is a large kind of waxy hydrocarbon. And it's very, very durable, hard to dissolve, whatever. The part that we're going to be talking about is these microinclusions. They're hard to see. You don't see them optically. You don't even see them in electron microscope with the secondary electrons, but you can observe them using backscatter. And that was used sort of to mark them off so that we could take them and analyze them using these scanning probe techniques. So we used two techniques. One was a nano-IR. Nano-IR uses some of these principles, which we heard already in this session. You can create kind of a enhanced field at a sharp metal probe close to a surface, so you can be in the near field and look at IR spectra with resolution which is way, way below the diffraction limit. And this can be done either in the form of taking a spectrum of a certain point in the surface, or by locking in on a particular wavelength and mapping out the spatial distribution of that chemical species which is represented. So we see a result of that here. What we see here are the amide 1 and the amide 2 peaks, which are very, very prominent in those organic micropools. If we look outside in the flint, then you don't see them all. You only see them within those organic micropools. The results are tabulated here to the side. We see both the amide 1 and the amide 2 peaks. The amide 1 can be broken down into its structural components, whether it represents structurally a beta sheet or alpha helix or random coils. And as you can see, we really did not see anything which could be corresponding to beta sheet, but we did see something which looked like the alpha helix and some random coil. This is shown in these mappings. Here on the right-hand side is the wavelength corresponding to the alpha helix. You see it more or less covers that area of the microinclusion. And down below is the area of the random coils that more or less overlaps, but you see the spatial distribution is more sparse, and it is of a lower intensity than the one above it. On the other hand, the peak for the silicon oxide shows that it's completely absent from the area of the microinclusion. Okay, so we have some chemical information here. Now we want to go to the mechanical information. Anyone who's done some mechanical work with AFM knows that one way to do this is to push a tip into a surface, look at a deformation, and try to correlate the deformation with the force and convert that into an elastic modulus. But when you have a really stiff material, as the things that we're looking at, the difference between this line of no deformation and the bowed one with the deformation, it becomes very, very small. And you have a huge amount of uncertainty. So rather than using these kind of quasi-static measurements, we use a technique called acoustic atomic force microscopy, where what you're looking at here is contact resonances. And this is just showing here we have a free resonance of a cantilever. And here we have peaks, either first resonance, the second resonance. And these contact resonance peaks, once you're working with a certain applied force and a certain tip shape, its particular position is very closely related to the elastic modulus. That is, by measuring the peak position, then you convert that into an elastic modulus. So this slide shows a result of such a scanning probe measurement. This topographical view here shows the organic microinclusion. I want to point out that when we expose this to water or moisture, it swells, it noticeably swells. And furthermore, the elastic modulus drops very significantly. We were able to find these, by the way, by correlation with these fib marks which were made on the sample. Down here on the left, then we see the mapping of the modulus. The dark area is that microinclusion. The brighter area around it is the surrounding silicon oxide component. Macroscopic flint has a elastic modulus between about 60 to 120 gigapascals. Silica itself is around 70, 75 gigapascals, and that more or less corresponds to what we see in the area outside of the microinclusion. Inside the microinclusion, we see something much lower, which is around 30 gigapascals. That is actually still very large relative to what you might expect for proteins. Just to summarize that, and I'll get back to that, but I would like to say that we did show that using this technique, we can locate a specific region on the surface, analyze them chemically and mechanically, and correlate their behavior. The nano-IR, it shows us that we have an amide, which is predominantly in the alpha helix or the random coil. But if we look at the modulus values that we might expect to see when we have amides or proteins, they don't look like proteins, because something like collagen or other common proteins, they have a modulus which is about an order of magnitude lower than what we measured. On the other hand, there is a specific kind of protein assembly, the amyloids, which we heard from Louis in the morning session. They're in the form of beta sheets. And we saw from the IR that we do not have beta sheets here. Keratin, on the other hand, which I mentioned was probably a major constituent of the intercrystalline amorphous organic material, of course, it doesn't have any amide in it. So likely what we're looking at here is a protein which has been entombed and preserved within this stone for millions of years. We're really talking about tens of millions of years. And through cross-linking processes, it has become stiffer, and those processes have also helped to preserve the protein. So I hope what I have managed to show you is that this is just sort of, I could say, an in-progress report that is showing how using some of these nano in-situ techniques and correlating them with other information, there's a lot more which I don't have time to talk about here. We can really learn a lot about these structures, which otherwise would really be an enigma. It would be very hard to analyze them. I mean, you can try to leach out chemicals, leach out the organic material and analyze it, then you have no idea where it came from in the rock and what the morphology associated with it was. So with that, I think I'm on time. I would like to thank you for attention, and I'd be happy to answer any questions.
Thank you, Sydney. That was really nice. Any questions at this point?
Can I ask?
Yes, of course.
Sydney, is it possible that those organic materials, when they are held, you know, by the matrix, they become stiffer because of the surrounding and not so much because of the actual structure at point? So
the point of these kind of mechanical measurements that we do is they're very, very localized. Okay, so if you look at a typical contact radius that we're talking about, it's just a few nanometers. The depth of it is about 3 times that contact radius. So we're talking about something which is probing down into the surface really very minimally, maybe 10, 20 nanometers. And we know that the volume of the depth of those, the volume of those is much greater. So if you're asking, could there be some sort of a complex structure here? Well, sometimes it's presumed that these microcolonies, they come from microfossils. But in that case, you actually see in the microscopic images, you would see the siliceous outline of these skeletons of these microfossils. And those were not seen in these micropools.
Okay, so let's just thank Sydney again, and we'll move to the next speaker, who's Asmita Dutta from Ariel University. Okay, Asmita, can you share? Let's see that it's working. Good, if you can just move to the presentation mode so we can see this. Yes, great. So the stage is yours. You need to unmute.
Now I'm audible? Yeah, okay. Thank you. Thank you, Maya. Hello, everyone. My name is Asmita Dutta. I'm from Ariel University, working with carbon nanoparticles under the supervision of Dr. Ari Burenstein. Today, I like to present my work on surface modifications of carbon nanodots and its effect to increase the optical properties of carbon nanodots. This work is accepted for publication in Nanoscale Advance in this week. Before going into details about what is surface modification, first question comes in everyone's mind that what is carbon nanodots? So carbon nanodots are a new member of carbon nanofamily which has a size smaller than 10 nanometer. Its core made up of sp2 carbon implanted on sp3 backbone. How it is synthesized in our lab? In our lab, it is synthesized by bottom-up hydrothermal treatment of urea and citric acid solution. We take urea and citric acid solution in water and put it in microwave for 10 minutes. It is washed and cleaned after that for further use. About size, all I can say is that our lab synthesized CND has a size distribution from 10 nanometer to 70 nanometer, as you can see in the DLS graph. It has a spherical shape, as you can see in the AFM image. This. But the main reason why such tiny dot becomes so much attractive and interesting nowadays because of its strong fluorescence. The strong fluorescence is caused due to having the surface groups. We can tune the optical properties by modifying the surface groups. For this surface group, it's become water soluble and chemically stable. It is non-toxic and biocompatible in nature. It has different applications in several fields. It can act as photocatalyst, as size-controlled carbon nanodots has a tunable emission from near IR to blue wavelength. So it can act as a promising candidate for photocatalyst. The strong fluorescence can be sometimes quenched in presence of some metal ions. So it acts as a sensor for that particular metal ions. It can also act as a biomedicine and drug delivery system as it is non-toxic and biocompatible. It can produce the fluorescent spots inside the cell. That's why it can act as a bioimaging. It can reserve electrons, so it can act has huge application in photovoltaics and optoelectronics like LED. The optical properties of carbon nanodots is mainly differentiated into two parts, absorbance and fluorescence. We prepare two different types of carbon nanodots by varying the molar ratio of urea and citric acid. For one of them, it's 3:1 and another one is 1:1. As you can see clearly, the difference in the color of these two, the aqueous solution of these two types of CNDs in UV and visible light. Although we got two different peaks in the absorption spectrum, but in 3:1 molar ratio sample, the 405 nanometer peak become much more stronger and prominent. But in the another one, it is hardly visible. We also record the emission spectrum with 2 different excitation wavelengths and normalize it with the absorption spectrum, as you can see in this graph. To investigate the chemical genesis of the second peak at 405 nanometer, we add acetic acid as a carbon source as a precursor. We also prepared 4 different kinds of CNTs by varying the molar ratio of acetic acid with respect to citric acid and urea. In small concentration of acetic acid, the absorption intensity of both peaks is increased. It is quite unexpected and unnatural. But with the higher amount of acetic acid, it again started decreases. It may be due to the condensation of acetic acid to form acetic anhydride. Fluorescence intensity is also dramatically increased and significantly redshifted with the addition of the acetic acid. To explain the anomalous behavior, we did the chemical analysis. Chemical analysis is mainly done by 2 kinds of major experiments. One is FTIR, another one is XPS. In XPS, as you can see, there is a significant decrease in the C single bond O and C single bond C. However, there is a clear increase in the C double bond O and pi-pi star interaction on the surface of CND with the addition of acetic acid. Both from FTIR and XPS, it is confirmed that there is increase of oxygen at the surface of CND due to acetate ions. We also tried 2 different kinds of approaches for surface modification. One is annealing, another one is tying different pH solution. As you can see, in different pH solution from acidic to basic, there is a huge impact on the shape of the 340 nanometer peak. We remove C double bond O from the surface of the carbon nanodots by annealing, and in acidic solution, the double bond character of the C double bond O, COOH is also decreased. Comparing this to absorption spectrum, we can reinsure the fact that the effect of C double bond O emission on the 340 nanometer peak, as they both look very much similar. These are the 2 kinds of fluorophores which are responsible for the fluorescence behavior of the carbon nanodots. One of them is citrogenic acid, is responsible for the blue fluorescence. N-pi star transition of the CO bond is responsible for electronic excitation at 340 nanometer, which has an emission at 456 nanometer. Another one is HPPT. HPPT is responsible for the green fluorescence. NHCO, the 2-pyridine ring, is responsible for the electronic transition at 405 nanometer, which has an emission at 520 nanometer. From this above study, we can conclude that the green absorption peak at 405 nanometer is clearly observed in the 3:1 molar ratio sample, but it is hardly visible in standard 1:1 ratio sample. The amount of the C double bond O and pyridonic chromophore on the surface of CND is increased by the addition of acetic acid. pH and annealing also shows an impact on the shape of the 340 nanometer peak. With this understanding about the exact chemical origin of carbon nanodots, we can control the fluorescent property, and application utilizing the CNDs can be made more proper and efficient. I would like to thank my lab members for helping me and Dr. Ari Borenstein for his constant support. Thank you for giving me an opportunity to explain my work in front of you. Thank you so much.
Thank you, Smita. That was really nice. I encourage all of you to ask the questions in the chat, and we'll just continue for the next speaker for lack of time. This is Ashish Parajabati, and maybe you can share. Asmita, can you?
Yes, I will stop sharing.
Yes.
Yeah.
Perfect. Just for presentation mode, Ashish, if possible. Great. Yes, you're good to go.
1 minute. Yes. Okay. Good afternoon to all respected professors, dear colleagues, and all participants. I am Ashish Prajapati, doing my PhD under the supervision of Dr. Gilshalev in the School of Electrical and Computer Engineering at Ben Gurion University of the Negev, Israel. Today I'm going to present one of my PhD research work, that is omnidirectional absorption with some micrometer scale compound parabolic light concentrator arrays. The motivation of my work is based on fovea centralysis, which is a closely packed vertical arrays of inverted cone photoreceptor cells located in the retina that is responsible for high acute binocular vision. The cones are operational in well-lit environments and are responsible for light trapping the impinging illumination. Based on this motivation, Gil-Shalev and co-workers presented the vertical light funnel arrays as a light trapping technique for photovoltaic application that is bio-inspired by properties of fovea centralysis. They shown 65% absorption enhancement compared to silicon film of identical thickness, and also shown a power conversion efficiency that are 60% higher than those of optimized nanowire arrays of same thickness. Other motivation of my work are light matter interaction, absorption based photonic devices, photovoltaic applications, and potential efficiency enhancement in ultra thin PV cells. Based on my motivation, myself and co-worker have studied light trapping mechanism in LF substrate complex, in trumpet or hyperboloid, in ellipsoid, in compound parabolic concentrators, and in light funnel based PV cells in detail, and shown a significant broadband absorption efficiency enhancement that leads to higher power conversion efficiencies. The broadband absorption efficiency is the absorptivity averaged and weighted with standard air mass 1.5 global solar spectrum. For more details of these work, please go through the below references, which is published in various different journals. In this study, we consider a substrate-less CPC array, which is in figure A, and the dimensions are presented here. The polarization of illumination is also shown, the electric and magnetic field, in which T along the X direction is shown for an example. Figure B presents an angle of incidence dependency of the CPC array, total absorptivity spectra, which is averaged of both polarization as well as polarization dissolved absorptivity spectra. And similarly for the corresponding spectra for nanopillars. These below color maps are for nanopillars and the above color maps are for CPC arrays. Evidently, the CPC array exhibit enhanced omnidirectional broadband absorptivity with peaks reaching wavelength greater than 800 nanometer. It's here. The peaks and spots is here present, but in the nanowire, it is absent here. It seems that it's is limited to wavelength 600 nanometer. Also note that while the angle of incident dependency of nanopillar absorptivity is homogeneous, the angle of incident dependency for CPC array is more complex and exhibit a hot spots like here, 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 here. Also, as expected, the absorptivity under TM illumination is higher and more omnidirectional than the absorptivity under TE illumination for both CPC array and nanowire arrays. Figure B also presents the angle of incidence dependency on total broadband absorption, TM broadband absorption, and TE broadband absorption for nanopillar array and for CPC array. The broadband absorption efficiency of CPC array is 30% here, higher for angle of incidence 0 to 80 degree throughout, and hence more omnidirectional with 10% minimum to 17% maximum variation for the nanopillar array. Broadband absorption efficiency of TE decreases significantly here for AOI greater than 50 degree, whereas broadband absorption efficiency for TM retains omnidirectional to angle of incidence till 70 degree. Similar responses is also recorded for nanowire, which is in black, and the red one is CPC array. To understand the absorption behavior, next, an analysis of spatial distribution of time average Poynting vector is presented. Figure A presents the spectral distribution in individual nanopillars and CPC arrays nested inside the respective arrays of where of the Poynting vector components, where Sx, Sy, Sz are the Poynting vector components. In this case, nanopillar array for all the AOI values, the lateral component Sx and Sy are considerably small, and most of the intensity is directed in Z direction, that is Sz. On other hand, for the CPC array, the lateral components are considerably high and of same magnitude as Sz component. This, of course, reflects the ability of CPC array to bend the light from normal to oblique direction into the lateral plane, and in this way to increase the interaction length between the impinging photons and arrays, with the resulting increase in absorption. Figure B and C shows the broadband values of lateral component, which is Sx, Sy, and vertical components is Sz, respectively. Evidently, the lateral component of CPC array are considerably higher, with values 2 times greater than the nanowire arrays. For AOI, angle of incidence 40 degree and 60 degree, and more than 80% for is higher for AOI 20 degree and 80 degree, which is indicative of the ability of the CPC array to effectively bend the light under broadband and omnidirectional illumination. On the other hand, the vertical components Sz of the array is very similar, except for the normal incidence, normal in which nanopillar prevails. Next, the conclusion. Arrays of sub-micron scale compound parabolic concentrators are elevated. Omnidirectional broadband absorption of solar radiation. Broadband absorption enhancement 30% throughout 0 to 80 degree. Strong light bending in vertical X sections. The broadband for lateral components is 80% higher than lateral component compared to nanopillar array. All the calculations are performed with FTTD simulations in Synopsys TCAD. I will be very happy to hear all your questions and suggestions at my mentioned corresponding address. Thank you very much for your valuable time, and be safe with COVID-19. Thank you.
Thank you, Ashish. So what I'd like to do, I'd like to open out the stage so that we can ask Ashish questions, but also the rest of the speakers, and have some kind of a discussion. So just please unmute yourselves and you can ask the question. And if not, I have questions that I'd like to ask, of course, that I've been waiting with. So do we have some questions from the crowd? Not at this point. Okay, so Sarah, I'm really happy that you're here. And I wanted to ask you, I looked at these wonderful tantalum sulfide structures and the oxygen, and I was wondering, you take the sample out every time, right? And you keep it outside to get it oxidized. Did you try to do this in prolonged times inside the TM? So obviously we've got some oxygen, we always see that. And to see this as it happens, something like a time sequence, although probably very expensive in microscopy time. I'm sorry to encourage you to do this.
Yeah, I think even as director of the microscopy center, I'd get in trouble if I kept my sample in for 3 weeks at a time. But I could try maybe. The samples are encapsulated by graphene, and so we knew the aging was happening even for graphene encapsulated samples. That isn't the case for the post-transition monochalcogenides. We found there that the graphene seems to protect the samples, or hexagonal boron nitride, and that we don't see any change in the optical, the Raman spectroscopy, or whatever else we're measuring, whereas the tantalum disulfide was different. So it must be that either it's the oxygen that is trapped beneath the graphene sample when we encapsulate it that is doing the aging, and that's a slow process in tantalum disulfide. Maybe it's much quicker in the post-transition metal chalcogenides, but we were trying to reproduce what the Gregorieva group had found in their electronic devices. And so for that reason, taking it out the sample and looking at the natural aging conditions in atmosphere seemed to be the way that we should be going. But for black phosphorus, we've done the equivalent. So we looked at what happened when you effectively create holes in the encapsulation layer, and in the microscope, you get a certain amount of degradation, but then it stops. Whereas when we take that sample out of the microscope, you get an additional amount of degradation, but it's limited to the areas that you've damaged in the TEM. So it forms this passivating layer. And we assume that some 2D materials form this passivating layer so that you don't get any more degradation, and some don't, if that makes sense.
I think that Reshef had these samples a few years ago. I don't remember if it was the work of Ala or Frida at this point. Maybe Ala is here, she can correct me. So he had some intercalation between the layers of alkali metals, I think. And the result was that you could get water inside the in between the layers. And I understood there was some issue that whenever you put it in the microscope and you waited, this would just go out because of the vacuum, and you wouldn't see this. So I thought maybe there are some effects that you could actually see under the beam. You know, actually, we now have the resolution that it wasn't there 15 years ago. It would be really nice to see if we could track these intercalation and all these kind of anion exchange reactions, I would call it, or oxidation, right? It's just that we need to find the ones with the right speed.
That's a great question, Maya. So we have done some work recently looking at that intercalation into 2D materials. It's not published yet, but that has absolutely shown that you could look on a timescale of a TEM, so a 4-hour or a 2-day, and you look at changes in the structure due to the de-intercalation of that materials. So yeah, I'll put you down as a reviewer. Thank you very much. Yeah, absolutely, there are reactions that happen on the right sort of time scale to be studied in a day or 2 or 3 days, you know, over a weekend in a microscope. Yeah, and I think that's sometimes we have to push them to be faster than they would be. So we use the heating holder, or we use a different gas. So we're looking at now trying to do more experiments in real reactive gas conditions. And on your other point of looking at water, we can do it, but we have to be fast. So you can get a wet sample in the microscope, and that layer of water does remain for a bit to be able to let you look at a hydrated surface or encapsulated hydrated surface for a little bit of time. So we've been doing that with another project, and yeah, yes, all right, it's a really good area, I think, that we could be looking at doing more in.
So that's great. I'll be waiting either for the review. You don't really have to, because I'll read the paper anyway also later. Do not worry. I don't want to ask questions for other people. I see some people already joined now. If you have something to ask or you want to comment, this would be really nice. Ernesto, maybe you have something?
Actually, I have a question for Ido Kaminer. I mean, the question that I asked was not well phrased. I asked if what kind of useful information. It was a bit egocentric the way I asked. I should have said useful for a material scientist. I mean, I'm sure that you get a lot of useful information in terms of physics, and your work is fascinating. But I'm wondering, as a material scientist, if your new techniques can provide important materials information that we cannot get about properties, materials properties that one cannot get by the standard TM methods.
So I guess the like optical excitations are, let's say, partially material related, but maybe not at the core of material science. We think about plasmonic resonances and stuff like that. Yeah. We see some work on phononic resonances, which is, I'm basically doing one step at a time from what is the optics side of material science to deeper into it. So phononic resonances, we saw there is a work by the Flanagan group in Minnesota where they bring a kick and they see how the material starts rotating, so or vibrating. And you see both the vibration, very fast vibrations on a nanoscale that can happen on you know, almost nanosecond timescales for something to oscillate. So So I think we can see effects like stiffness and how material deform on very fast timescales this way. On closer to my side is phononic resonances. You see phononic waves. There is a paper from 2017, 16, Nature Con that they had. It was the first time that we saw phonons moving inside materials. That is
so can you like image phonons? I mean, this is very interesting.
Mm-hmm. Yes, what they do is they bring a short pulse of light. It gives a very strong kick to the material, and that caused phonons to start to vibrate. It was also in some one of the TMDs, I forgot which one. And the phonons move inside, they change the layers, and then the electron image is deformed in a way that shows you the like bright and dark lines that are exactly matching to the wavelength of the phonon, and you can extract the group velocity of the phonon from that. So those are, I think, closer to what we're thinking about here.
Sure, sounds like that.
And I think there will be more effects of that type that we will see. We're starting to work in 2D materials in the microscope as well. So it's so I don't know the full answer. Basically, the main thing that limits us, what you would like to be able to see is, for example, take a lithium battery, operate it inside, and see dendrites or whatever processes happen inside, right? I don't know anything about this field. I just know it would be amazing to see that. Problem is that as long as the process is not repetitive, it's very hard for us to see it. We like processes that we can excite and repeat, and then measure 1,000,000 times per second. That's the repetition rate of our laser. So we collect enough signal by repeating the process again and again. And for that, phonons are great. But a process that is one time is much harder. It's not impossible. There was a Zewel paper on a one-time effect on 2 particles that were connecting together in the liquid and moving around. In one of the papers that came out after his death, I think it was 2018 Science. So and those were examples of the motion that was not repetitive. So it is possible, but much harder for us when it's not repetitive.
Mm-hmm. Thank you.
Okay, more questions maybe, or comments?
Yeah, maybe one more question to Ido. Ido, you showed the periodic photonic lattice. Did you also try to map defects in photonic lattices and their local band structure?
So not yet, but you're right. It's having a defect there as a way to confine light much more effectively is definitely interesting to try, but we didn't try that yet.
Yeah, that would be really interesting.
I actually had a question from my side to Sarah, or related to Sarah's talk on when we look at those Bilayers materials, the Moiré patterns that are, this is like getting enormous all around the world. I'm trying I'm curious what you think is like the frontier, where it goes next, especially from the side of the different kinds of excitons and excitations of different kinds in those materials.
So I guess, I mean, my expertise is in characterizing the structural variation. So I'd hesitate to predict what is going on with the excitons. And the sort of quasi-particle. I mean, recently there's been a lot of interest in Manchester going back to graphite, because they've produced rhombohedral graphite. You've seen that paper where they can now reproducibly tune the stacking in 2D materials using directional exfoliation. So when you do the encapsulation, you make sure you don't encapsulate the material along the armchair direction, so that you only do the zigzag direction, or the other way around, I've forgotten. And that means that then you don't end up changing the stacking back to what you didn't want. I think that is also a really large, something that could be really effectively applied in lots of other different systems. You know, we've done it in graphite, but there are lots of places where differences in stacking cause huge changes to the electronic structure. So I think that's a really interesting area. And I think that looking at more exotic twisted materials and different combinations of twist is also something that we're really interested in doing. Does that make sense?
Yeah, like different combinations of that, because from my side, at least, I like seeing the structural effect that happened there, like is something that we are like an order of magnitude away in resolution. So we cannot really see it on the scale that you were showing.
But you said tens of nanometers was feasible, did you? That was a question that I had for you. Because if you
we did 10 nanometers. What limited us so far was the fact that there were no features small enough. The photonic crystal structure that Lothar also mentioned, the whole was 300 nanometers. So we need small enough features to see something smaller. The best that was shown so far was about 6 nanometers by this Wellbrook. And there was a nanoparticle that had a field that was decaying much more quickly next to it. I'm sure that we'll see a nanometer will still be in range, especially once we start doing more STEM fields connected with this method. And the Rocket is doing a bit on this.
A chat, because we can certainly pattern all kinds of structures into the materials at any scale that you like, really.
Yeah, I know the fringes coming from the Moiré pattern at similar scale. So even if we cannot see individual atoms there, maybe we can see the fringes from the Moiré.
Absolutely. But we've also done etching where you can, because it's encapsulated, you can preserve etched structures. So you can use the STEM probe to etch whatever patterns and shapes that you like. So there's been other reports showing you can do ribbons, but actually I think ribbons are not very stable when you take them out of the microscope. By having our samples encapsulated in something like HBN, you have an electronic structure that you can pattern with the STEM probe, but then you preserve within a HBN sandwich, and that means it's then transferable and postable. So maybe we should have a chat with the other physics people that I work with and work out some experiments to do in your machine.
Yeah, that's interesting. So like you basically do fabrication with the STEM probe too.
Yeah, so I have a STEM probe that is 2 nanoamps. It can drill through steel. It can drill through TEMs with no problem at all.
Wow. And you can pattern, like, for example, the phononic band structure or something like this.
Yeah, and we've shown that you can also do that in our e-beam. So we have 100 kV e-beam. So obviously the STEM probe is fine if your sample is suspended, but we can design protocols in the scanning transmission electron microscope and then apply them in the 100 kV e-beam and use, it's a slight sacrifice in resolution. So in the STEM, we can get resolutions, patterning resolutions of a nanometer or a little bit better once you take it out. Whereas in the e-beam, you're more like 5-10 nanometers, but still you can develop the protocol and actually see what you're doing in the STEM and then apply that in the e-beam. And we've shown that the contacts, so we can cut contacts, and the patterns that we draw are completely electrically insulating. So it does seem to be something that we could try.
Because one of the biggest holy grails in this field, if we think about polaritons in 2D materials, and it started with graphene plasmon polaritons. But now people see this in many other materials like non-polaritons in HBM. So those are considered like a very strongly confined modes of light. What is really exciting there is that you can take a 5-micron infrared light and confine it into a plasmon that is maybe 50 nanometers. So like a factor of 100 easily. And people are now curious whether you can get to polariton wavelengths of sub-10 nanometer, like a few nanometer wavelengths. And the reason this is not easy to do that is that when you couple the light into it, it doesn't couple into the material effectively. It's too different. It's called momentum mismatch. So if you have the ability to do fabrication on a single nanometer scale, you can make like a grating with periodicity of a few nanometers, like lines, and that will help light that we can shine on it, couple into modes that propagate inside the material. And that will solve this problem of so far people cannot excite that exactly for this reason.
Good.
So maybe that's something to think about doing.
I'll send you an email.
Yes.
Okay, so we are towards the end of the discussion, although I don't want, it was kind of nice, I don't want to send people away. But we have now something like 20 minutes of break, and then we have another plenary session. So I would like to welcome everybody to come again and hear Paul Weiss from UCLA. And thank you all for being here, and I hope to hear you again and again. Good. So bye, everybody.
Bye, Maya.
Bye, thank you, Maya.
Bye.
Maya.